Welcome to this second week. We are covering first Unit 5 and then Unit 6. Unit 5 deals with functions of several variables. That's what multivariable calculus is about. So let's get started with functions of two variables. You're all familiar with functions of one variable. When you have a function of one variable, you already go into higher dimensions. You draw it as a graph in the two-dimensional plane. That's what you're very familiar with. And when we have a function of two variables, we can still draw it. We can draw it as a graph. So the graph is then a surface in three dimensions. In this case, you just see there are parabolas as traces and ellipses as traces. Traces are intersections with coordinate planes. And if we kind of just know what we are doing, this is a paraboloid. Like here, this is an example of a paraboloid. And then we have the contour curves. This is just in the xy plane. If fxy is equal to 0, then we have seen that we have that ellipse here. And that's what we also see here, right? So this is this ellipse here. We cut the graph at z is equal to 0. So this means x squared over 4 plus y squared over 4 is equal to constant. These are ellipses. And we have z is equal to x squared minus y squared. That's a very important case. And I have here just a model which shows this saddle. This is the hyperbolic paraboloid. We will talk about this a lot. For functions of three variables, we can no more draw the graph. That would be the graph in four-dimensional space. We cannot draw that. But what we can do is we can still draw the level surfaces. And so when you look at a function of three variables and you draw this level surface, you can imagine have something like this. These are all these level surfaces are together, like with this doll here. So this is one level surface, which the function is constant, one constant value, or you have a different value here, or again a different value. Quadrics are just a special case. These are quadratic surfaces. Let me just write you down the simplest cases here: elliptic and hyperbolic paraboloids. So that's the hyperbolic, the one-sheeted hyperboloid which we have here. Pretty cool. So you see that here. And then there is x squared plus y squared plus minus c squared is equal to minus 1, which is a two-sheeted hyperboloid. So the two-sheeted hyperboloid looks a little bit like this. It has two sheets. It's like this perfect ellipsoid I found, brought from Cape Cod. And then there are very important special cases which are like x squared plus y squared is equal to 1, x squared plus y squared is equal to z squared. So we have seen functions of two variables, plot, 3D, and then I say x squared plus y squared. And then I can say from where to where I want to see it. For example, that paraboloid, too much. So that's the sphere. It's a little bit too, maybe I make it 4 so that it's larger. That's the sphere, and we have seen the one-sheeted hyperboloid. That's now kind of a little bit, I have to zoom out a little bit so that it's kind of more clear here. So that's the one-sheeted hyperboloid. When I take a minus 4, I get a two-sheeted hyperboloid. And when I get the 0 here, then I get the beautiful cone. But you can just experiment yourself with with other surfaces. Like, for example, I just multiply here with some, I don't know what this gives. This gives me a different surface. So this is a surface which is a cubic surface, quite beautiful. I can even make, instead of manipulate, I can say animate. And then it should actually kind of, it should produce a little movie. Okay, here's the summary of Unit 6, where we look at parameterizations of surfaces. And the first thing we have to look at is polar coordinates. Polar coordinates are another way to describe points in the plane, in the two-dimensional plane, and you just write the definitions of the cosine and sine functions, r cosine theta and r sine theta. So this defines a point in the plane. And you can also express r or theta then from x and y, even so that's with a grain of salt. But then in spherical coordinates we have three coordinates. We have the theta angle, which is the same. Then here we have the phi angle, which is the angle from above. You see that here. So we have the angle phi, which is the angle from the z-axis, and then we have the distance from the origin, which is rho. So using these two pictures here, these are very important pictures, because this is from above and from the side, so above and side view. So this r is the distance to the z-axis, and it's not used in the spherical coordinates, but it helps us to write this as r cosine theta, r sine theta, and then z is equal to rho cosine phi, which you see here. And you can immediately write down the parameterization of a sphere then. So you have a sphere is described now by two parameters. Usually fix that. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. Phi angle here goes from 0 to pi. Also important are surfaces of revolution. In this case, the radius r is given as a function of z. And we look at more examples in class, but let me just illustrate that again with my computer here. So when I'm parameterizing a surface, I say parametric plot 3D. And for the sphere, I have seen that this cosine theta, I just take t, and sinus s, let me just write that down, sinus s cosine theta, and then sinus s sine theta, and then cosine s, and t goes from 0, theta goes from 0 to 2 pi, doesn't matter what letter we use, and s goes from 0 to pi. It's a beautiful sphere. It's a parameterization. So parameterization is a rule which gives us from two parameters, s and t, it gives us a surface. If you want to kind of experiment a little bit, we can change the parameters and we get a different surface. And I take here from 0 to 2 pi. What I get is just a surface of revolution. In this case, I get these beautiful waves. So that's an example of a surface of revolution. Donut. Yes, that's a donut here.